For our final project, we chose the diabetes prediction dataset. Taking a look at the data, we can see there are 9 features: gender, age, hypertension, heart disease, smoking history, BMI, HbA1c levels, blood glucose levels, and finally the diabetes feature. And when we check the shape, we can also see there are 100,000 entries. The first step we took was cleaning the data. When we ran a check for empty values, we were fortunate enough that this dataset didn't have any null values. There were, however, duplicates, 3,854. These we could easily remove from the dataset. Also, the feature gender had 18 entries of the value other. We removed this because they didn't provide any significance to the models that we used later, and from later visualizations, we can see that gender itself as a feature was not that significant. For the first bit of preprocessing, the gender feature was converted into a numerical category, 0 or 1. Also, all the values in smoking history were changed to be their own features, as you can see from the image above. No info, current, ever. These values become smoking history, no info, smoking history, current, etc. They become features. And they hold the values true or false. These 2 changes later made it easier for visualizations and for model training. The first visualization we have here is the correlation matrix. A correlation matrix shows the correlation between all features. Here we can see which features affect a diabetes diagnosis. Smoking history, no info, has a negative correlation to diabetes, and all the other smoking history features have a less than 0.10 correlation with diabetes. Also, because entries had no smoking history info as their value, which was almost half, this would create a lot of imbalance and inaccuracy when we train our models. Thus, we removed smoking feature entirely from the dataset.
This scatterplot plots a person's diabetes result as a function of their age and BMI. As you can see, the general trend is the higher the age and the higher the BMI, the more likely someone is to have diabetes. However, there's also many outliers in the scatterplot, so we have removed them, as you can see here. The diabetes data in our dataset is very imbalanced. There are more than 10 times as many entries that are diabetes negative than there are entries that are diabetes positive. However, knowing that someone is diabetes positive is more important than knowing when they don't have diabetes. So how do we fix this? It's pretty simple. We either have to add or remove data. However, if we removed diabetes negative entries until the data was balanced, there would not be enough data to train on. So we have to create new entries by interpolating already present diabetes positive entries. To do this, we're using a technique called SMOTE, standing for Synthetic Minority Oversampling Technique. It creates new data by choosing a random point on a line between a minority class point and its closest neighbor, which in this case would be a point that is diabetes positive and its closest neighbor that is also diabetes positive. As you can see here, on the left is the confusion matrix before balancing, and on the right is after balancing. The rate of false positives and false negatives has gone down.
After all the pre-processing and cleaning, we are left with this as the final dataset that will be passed through all the 3 different models. The random forest model works by creating a series of decision trees that are all then merged to create a more accurate result than just a singular decision tree. From the results, we can see that the accuracy, precision, and recall of this model was 0.98, with a true negative count of 17,000 and a true positive count of 427.
Logistic regression works by assigning probabilities to binary outcomes using a function that takes a continuous value of arbitrary range as input and outputs the probability as a value between 0 and 1. The binary value is then determined by some probability cutoff, where a value below the cutoff corresponds to one binary value and a value above the cutoff corresponds to the other. It is similar to linear regression, except it can classify binary or discrete variables rather than continuous ones.
Last but not least, we take a look at naive Bayes algorithm. Naive Bayes algorithm is a probabilistic machine learning algorithm based on Bayes' theorem. It is particularly suited for classification problems, such as predicting whether an email is a spam or not, or in our case, predicting whether a person has diabetes based on certain features. How naive Bayes makes prediction: given a set of features, for new instance, the algorithm calculates the posterior probability for each class. The class with the highest posterior probability is predicted as the output. Key advantage of naive Bayes algorithm is that it's simple, it's efficient, and it works well with categorical data, but it also has some limitations. It has an assumption on independence. It's sensitive to feature scale, lack of probabilistic interpretation. In general, the best model in our case was random forest. It combines multiple decision trees for robustness. It handles complex relationships over drifting, provides feature importance, insight, and achieve higher accuracy and AUC and ROC in the evaluation, making it a strong performer for the given dataset. So at the end, random forest wins in terms of accuracy.